We're here at QCon London 2012, and I'm sitting here with Rupert Smith. Rupert, who are you?
My name is Rupert Smith, and I'm currently working for Rapid Edition. And myself and Kevin Houston have been here today giving a talk on our fix engine, specifically looking at low latency performance.
So why don't you like latency?
Latency can mean you miss your trades. Basically, if somebody's selling something in the market, you've got to be the quickest to get to it if you want to be in with the chance. It's not necessarily about being the quickest. We were talking before about it's about making the software real time, which simply means making it more predictable. Because there are things like garbage collection and other sources of jitter that might mean that you have a certain chance of missing a trade. So even though a fix engine might perform quite well and have low latency, there'll always be that section of high latency outliers that you might run into. So we initially started out with the aim of just making the fix engine more predictable and removing the high latency outliers. But what we actually found is that we managed to lower the sort of latency baseline as well. So it's about being able to give people predictable execution and to avoid running into latency spikes.
So what's your approach to avoiding these? But do you use Java?
Well, the fix engine I've written was originally written in C#, and prior to this I'd worked on Apache Qpid, and I'd had various ideas about how messaging software should be written. I hadn't necessarily been able to apply those ideas at the time when I worked on it. So when I went to be interviewed at Rapid, they told me about their ideas. So we kind of merged our ideas together, really. So a lot of the ideas that I've implemented are not my own. They already existed in the C# engine. So the one thing that they suggested doing, which is quite controversial, is to make the engine garbage-free. The whole point of C# and Java is that these languages have garbage collectors, so you can just allocate objects and you don't have to worry they get cleaned up after you. But obviously, every time the garbage collector runs, it can pause your program and inject latency into it. So they suggested that we write it so it's garbage-free. When Java first came out, we might be talking pre-Java 1, people actually used to make the programs Java-free because the object allocation was very slow in some of the original versions. But now, doing object pooling, for example, is considered to be an anti-pattern, something you shouldn't do. It's going to make your program slower. Mm-hmm. So it is quite a controversial thing to attempt to do.
So did you do it? How did you do it? Did you use object pools, or did you rewrite your code to just use primitives?
Well, we've got a sort of hierarchy of 4 different techniques, because the Java compiler itself is smart enough to eliminate some of the garbage. So if you allocate an object, say, within just one method, and then you don't return that object, the compiler will say, well, that object never escapes from the scope in which it's in, so I can just allocate its fields on the stack, and then it never has to get allocated on the heap and cleaned up afterwards. So usually I write the program, and then I run it under a profiler and only eliminate the garbage that actually is there. Which might be specific to a particular implementation of Java, because there's not just the Oracle JDK, there's IBM and other ones as well. So I've just gone for Oracle Java. So that's the first thing we do, is just let the compiler take care of it. The second thing you can do is you can make your objects mutable, so you can change the fields. But generally that's bad programming practice. All the libraries in Java are immutable when they can be. So for example, if I pass a string to a method that you've written, if your method were to change the string and not tell me, that would be very annoying. But what you can do is make an object mutable, and then you can just reuse it by changing its fields at a later point in time, which means that you're more likely to introduce bugs into your programming. Makes it more tricky. So it's not necessarily a nice thing to do, but it can help you save on garbage. The next level you might go to is object pooling, which basically is mutable objects that you just keep in an array somewhere. You take some out, use them. When you finish with them, you put them back again. So you might use that in a situation where you don't know how many you need in advance. And then the highest level technique would be reference counting, where you need to pass data from one thread to another. So if you had 2 threads that are operating on the same data, you don't know which one's going to finish first. So just whenever the reference count goes back to 0, you know they've both finished, and it's safe to stick it back in the object pool. So in fact, we don't actually use object pooling very much. Object pooling on its own is only used in one place in the code, where I don't know how many of a particular kind of object I've got to allocate. And the reference counting is really only used, well, it's used mainly on the actual fixed message objects, where they're being handed between one thread and another.
But do all of these techniques do they actually? They don't actually guarantee that there will never be a garbage collection, because there might, if you use a library that might do some naughty things, there might still be.
Well, there's no third-party open source code in our fix engine. We wrote all the libraries that we use ourselves. I've obviously used what's in the Java standard library, but I mean, if you're trying to be garbage-free, you might run into problems because you'll use something in the standard library and it's not actually garbage-free, so then you've got to write your own implementation.
Oh, really?
And, yeah. I've been fairly lucky with that, and it caused me a few headaches, but mostly I was able to work around them.
So you really always, okay, so you can you basically have to look at all of the data paths, code paths, and see if if they contain any new operator, basically.
Well, new is okay if you're going to hang on to the object for a long time. It's when you're creating stuff and then throwing it away quite quickly that it's the problem. Well, if I'm trying to make some code garbage free, what I generally do is run it under JProfiler and just look at the allocation hotspots, and that will tell me where objects are being allocated continuously, how much memory they're using, and so on. So I can focus down quite quickly on where the garbage collection is going. Generally, I also run it. There's some command line options with Java. You can put -XX : plus print GC, and it will print out on the console information every time it's doing a garbage collection. So I'll run it with that as well and just check that it's not actually running the garbage collector. And do things as well, like leave it running for a weekend, come back in on Monday, check that it managed to keep running all weekend with no garbage collections.
So that's very interesting. That's a very pure code approach to low latency, basically, or no GCs, basically. And so you don't use any kind of real-time. Have you used real-time virtual machines?
No, I haven't at all, because the real-time virtual machine will let you allocate things on the stack. I think the real-time Java VM is not free, though, so if we produce the version that was for real-time, that might put people off attempting to use it, because then they've got to buy the real-time version. So, yeah.
So you're doing interesting things with FPGAs, so programmable hardware. Why do you need that? Isn't the CPU good enough?
The CPU is pretty good. CPUs are very fast, and I mean, if they're clocked at, say, up to 4 gigahertz, an FPGA might only be clocked up to about 600 megahertz. But you can do things in parallel in hardware that you can't do in software. So even despite the lower clock speed, you can actually get a speed up if you target your hardware implementation towards a very specific problem that you're trying to solve.
So what kind of problems do you solve with the FPGA?
Well, I suppose one thing is the serialization and deserialization of the message, which we've written in software. That is, well, Fix is an ASCII-based protocol, and we're constantly converting the ASCII message into binary format to give it to an application. So you'd write your trading application, it expects the price, for example, to be a decimal number. It doesn't want it in ASCII. And then likewise, when it's sending out its order, that's going to be converted back into ASCII. So we're going to be implementing the ASCII to binary and binary to ASCII part in hardware, aiming to do that as quickly as possible. So, for example, in software, a cycle around that loop might take about, say, 8 microseconds. In hardware, looking to get that down to much less than that.
So how do you actually use the hardware? Do you write Verilog or something?
Yeah, it's all written in Verilog. I'm not actually doing that. Someone else is the hardware guy. So.
Okay, that's always good. Right.
Don't ask me too many questions about that.
So how do you design for an FPGA? I mean, how do you have different algorithms, or how does that work?
Well, the FPGA is really cool because a program for FPGA written in a hardware definition language, the entire thing runs in parallel. Every line of code is simultaneously executing. It's quite a bizarre thing to get your head around to begin with. Once you begin to understand it, you think, wow, this is really cool. But
so do you have, with an FPGA, do you have to write everything from scratch, or can you use libraries for third-party things?
There are libraries for things, but it's not quite like software where you've got a lot of libraries. You are doing some very primitive operations with bits, and I mean that's why it can be fast, because you're literally designing an electrical circuit made up of gates, ultimately, that's juggling bits, so you can get right down there to the lowest level of detail and tweak everything just how you want it. Basically, the Fix engine has 3 layers. It's got a session layer on top, which handles things like logons and heartbeat messages for you. Mostly messages just pass through and are given to the application. And then below that, it's got a translation layer that does the serialization, deserialization between ASCII and binary. And then below that, we've got a network layer. And what we're doing is moving the bottom two layers of that stack down into hardware. So the message will arrive over the network, be turned into a binary format, and then handed straight up to the session layer, which really just passes it onto the application. So it'll be like zero copy I/O. There won't be any copying going on internally in the stack. During my talk, I had a slide that shows you some of the copying that can actually go on between the network card and by the time the information arrives at the application level internally within the stack, within the TCP stack itself and within the fix engine. So we'll be eliminating all copying so that the data will just directly be handed over. There's other things we can do in hardware that we can't do in software, like cut-through. TCP is not really designed for cut-through because there is a message length and a checksum in the header of the message. So you can't write those things out until you've finished writing the body of the message because they go at the beginning. But when a message is arriving over the network, we can certainly stream that message into the fix core straight away before we even have received the last bit of it off the network. Just that if we encounter an error in the message later on after we've already started passing it into the fix core, we need to send up a signal saying, hey, that last message is corrupt, by the way, and forget that last one. So even though the protocol is not really designed with cut-through in mind, there are tricks we can do to get at least some kind of cut-through on it. Likewise with the PCI bus itself, the PCI bus protocol is not really designed for cut-through. I'm not actually too familiar with the format. I just know that it doesn't. Well, I read a paper comparing the PCI bus to hypertransport bus, and hypertransport was designed with cut-through. So, for example, in hypertransport, you'd have a header on your message, then the message body, and then a tail at the end, and you put the checksum and so on in the tail at the end, so you don't need to know it up front before you start sending the data. And I don't know for certain, but I think the Intel QPI bus is also much better designed for cut-through. But we can do a similar trick when you're sending a message, you put it on the PCI bus. We can start feeding that into the fix core straight away. We may find out that message is corrupt and have to cancel the operation, but at least in one direction we're getting some use of cut-through. So that lets us sort of merge the layers of the stack together a bit and have them running in parallel. So that's where we'll get an advantage with FPGA.
That's a very powerful solution.
Yeah.
Right,
yeah.
okay.
You can't do these things in software. You don't have that option.
Because you need signals basically
Yeah.
to race ahead and then...
Yeah.
Okay. Oh, that's very useful.
Yeah.
Right.
And Intel have been very helpful. And of course they have their QPI bus as well. And they've been quite keen to promote that to us as an option. And so the idea is you'd have a network card. The network cable goes straight into a little board which actually plugs in a CPU socket and is talking directly to the bus. And that would be a lower latency solution that we can get on PCI.
Oh, okay.
But the implementation we're doing now on FPGA is going to be on the PCI, on a PCI card.
So these are all very useful techniques, and I think we should all check out FPGAs for our low latency.
Yeah, no, I recommend getting a book and having a read. It is really quite a fascinating thing. Although I'm not doing the hardware implementation, someone else has been employed to do that. I did find out quite a lot about it in advance,
right.
So I can understand it. And yeah, I was quite blown away by what you can do. It's quite a cool thing.
So it seems to be a new venue for well, a lot of things.
Yeah.
Right.
Yeah. I mean, you can buy like a Xilinx board on eBay for $30 or something, a really basic kind of starter board and a book, and have a play around with it. So.
But you have to learn Verilog or VHDL.
Yeah.
But it's a high level-ish language. It has coded braces.
I think VHDL is considered to be sort of a bit more high level than Verilog. It has like a type system. I don't actually know VHDL. Verilog is considered to be a slightly lower level, get down and dirty kind of language than VHDL. So.
Well, we'll all have to get out our old hardware description books, and thank you, Rupert Smith.
Thank you very much.